Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
13th century astronomy grappled with significant challenges. Prevailing models, largely inherited from Ptolemy's al-Samarqandi, struggled to accurately predict the observed positions of celestial bodies. The geocentric model, placing Earth at the cosmos's center, faced increasing strain as observational data accumulated, revealing inconsistencies between theoretical predictions and the actual movements of planets. These discrepancies spurred astronomers to seek refinements and adjustments to the existing framework, aiming to reconcile theory with the ever-growing body of empirical evidence. Jamal al-Samarqandi emerged as a prominent figure in this era of astronomical inquiry. His work, particularly his Tadhkira film al-Urdi, or Memorandum on Astronomy, exemplifies the efforts to improve upon Ptolemaic astronomy through a rigorous application of mathematics and observational techniques. Samarqandi's central aim involved addressing the nagging disagreements between established theoretical models and the observed phenomena in the heavens. He sought to create a more accurate and internally consistent model of the universe, one that could better account for the complex motions of the planets and the moon. Within the Tadhkira, Samarqandi meticulously examines various aspects of the Ptolemaic system, identifying areas where improvements could be made. One concrete example lies in his detailed discussion of the lunar model. The Ptolemaic model of the moon's orbit, with its epicycle and deferent, had long been known to produce inaccuracies, particularly in predicting the moon's distance from Earth at different points in its orbit. Samarqandi, following in the tradition of earlier Islamic astronomers, explored alternative geometrical configurations and parameter adjustments to minimize these errors and bring the model into closer alignment with observational data. He delved into the intricacies of the lunar parallax and its impact on determining the moon's true position, demonstrating a keen awareness of the challenges inherent in accurately modeling the celestial body's motion. Samarqandi's astronomical pursuits were deeply intertwined with the intellectual environment of the Maragha Observatory. This institution, established in Persia under the patronage of al-Urdi Khan, served as a hub for astronomical research and innovation during the 13th century. The observatory provided Samarqandi with access to state-of-the-art instruments, a vast library of astronomical texts, and a community of scholars dedicated to advancing the field. The collaborative atmosphere and the emphasis on empirical observation at Maragha profoundly shaped Samarqandi's approach to astronomy, fostering a spirit of critical inquiry and a commitment to refining existing models through rigorous mathematical analysis. Nasir al-Tusi, a towering figure in Islamic astronomy, exerted a significant influence on Samarqandi's work. Al-Tusi, who directed the Maragha Observatory, spearheaded a comprehensive reevaluation of Ptolemaic astronomy, challenging some of its fundamental assumptions and proposing alternative geometrical models. Samarqandi, as a member of the Maragha school, benefited directly from Al-Tusi's insights and research program. He built upon Al-Tusi's earlier work on planetary models, incorporating his ideas into his own Tadhkira and further developing them through his own independent investigations. Al-Tusi's emphasis on precise observation and mathematical rigor served as a guiding principle for Samarqandi's astronomical pursuits. Samarqandi's contributions, in turn, resonated with later scholars, including Ibn al-Shadiya, a 14th century astronomer working in Damascus. Ibn al-Shadiya's astronomical models, particularly his models for the moon and the planets, exhibit striking similarities to those developed by the Maragha school. There is strong evidence to suggest that Ibn al-Shadiya had access to Samarqandi's Tadhkira or other works from the Maragha tradition, and that he drew upon these sources in formulating his own innovative astronomical theories. Ibn al-Shadiya's models, which eliminated the need for Ptolemy's equant, represent a significant step toward a more geometrically consistent and accurate representation of planetary motion, demonstrating the enduring impact of Samarqandi's work on subsequent generations of astronomers. This exploration will cover Samarqandi's multifaceted contributions to the scientific landscape of his time. It will delve into his astronomical contributions, focusing on his efforts to refine the Ptolemaic model and address discrepancies between theory and observation. It will also examine his significant work on geometric optics, exploring his investigations into the nature of light and vision. Finally, it will trace Samarqandi's influence on later scholars, highlighting the ways in which his ideas shaped the development of mathematics and science in the centuries that followed. Samarqandi's intellectual journey led him to grapple with the intricacies of the cosmos, specifically the challenges inherent in the Ptolemaic model of the universe. Ptolemy's al-Samarqandi provided the bedrock of astronomical knowledge for centuries, yet it presented certain inconsistencies that demanded resolution. These inconsistencies primarily concerned the observed variations in the speeds and positions of the planets as they traversed the celestial sphere. The intellectual problem lay in reconciling these observations with the prevailing Aristotelian physics, which posited a universe of perfect, uniform circular motion. Planets, according to Aristotle, should move at constant speeds along perfectly circular orbits centered on the Earth. Samarqandi, like other astronomers of his time, sought to preserve the fundamental principles of Aristotelian cosmology while simultaneously accounting for the deviations observed in planetary motion. His approach involved a meticulous examination of the existing observational data, coupled with sophisticated mathematical techniques designed to refine the geometrical models used to represent planetary orbits. He delved into the complexities of epicycles and deferents, the primary tools employed by Ptolemy to explain the non-uniform motion of celestial bodies. The Ptolemaic system utilized a combination of these theoretical constructs. A planet was thought to move on a small circle, the epicycle, whose center moved along a larger circle, the deferent, centered ideally on the Earth. To further complicate matters, Ptolemy introduced the concept of the equant, a point offset from the center of the deferent from which the center of the epicycle appeared to move at a uniform angular speed. The equant, while effective in predicting planetary positions, violated the principle of uniform circular motion around the center of the deferent, introducing a degree of mathematical artifice that troubled many astronomers. Samarqandi's work aimed to address this very issue. He scrutinized the parameters of the Ptolemaic model, meticulously adjusting the sizes and orientations of epicycles and deferents to achieve a better fit with observational data. His efforts, documented in his Tadhkira, reflect a deep engagement with the quantitative aspects of astronomy. For instance, he revisited calculations related to the eccentricity of planetary orbits, seeking to minimize the discrepancies between predicted and observed positions. To illustrate, consider Samarcandi's treatment of the planet Mars. The motion of Mars presented a particularly challenging case for Ptolemaic astronomy due to its pronounced retrograde loops and apparent backward motion against the background stars. Samarcandi meticulously analyzed the observational records available to him, including those compiled at the Maragha observatory, to refine the parameters of Mars' epicycle and deferent. He adjusted the radius of the epicycle and the eccentricity of the deferent, employing trigonometric calculations to determine the optimal values that would minimize the difference between the model's predictions and the actual observed positions of Mars at various points in its orbit. These calculations were far from trivial. They involved solving complex trigonometric equations and employing iterative methods to converge on solutions that provided a satisfactory level of accuracy. Samarcandi's Tadhkira details these computational procedures, providing a glimpse into the painstaking efforts required to reconcile theory with observation in pre-telescopic astronomy. The Tadhkira served as a comprehensive handbook, detailing not only the theoretical framework of astronomy, but also the practical techniques needed to perform astronomical calculations. He revised planetary parameters, offering corrections to the mean motions of planets and refining calculations of planetary latitudes. His adjustments to the Ptolemaic model, while remaining within the geocentric framework, paved the way for more accurate predictions of planetary positions. While Samarcandi did introduce a novel approach to planetary models, his work remains squarely within the tradition of Ptolemaic astronomy. He sought to refine and improve the existing model, address its shortcomings, and enhance its predictive power. The significance of Samarcandi's astronomical work lies not in a radical departure from the Ptolemaic system, but in its rigorous application of mathematical techniques to improve the accuracy of astronomical models. His efforts represent a continuation of the scientific tradition established by Ptolemy, a tradition characterized by commitment to both theoretical consistency and empirical validation. Samarcandi's contributions had a direct influence on subsequent generations of astronomers, most notably al-Urdi, the Timurid ruler and astronomer, who established a renowned observatory in Samarkand. Al-Urdi's astronomical tables, considered among the most accurate of their time, bore the unmistakable imprint of the Maragha school's tradition, a tradition in which Samarcandi played a significant role. Al-Urdi's astronomers, building upon the work of their predecessors, continued to refine astronomical parameters and improve the accuracy of planetary models. The observations and calculations made at al-Urdi's observatory provided valuable data for later astronomers, contributing to the gradual accumulation of knowledge that eventually led to the scientific revolution. The meticulous attention to detail and the commitment to empirical observation that characterized the work of Samarcandi and his successors stand as a testament to the enduring power of the scientific method. Samarcandi's efforts to reconcile Aristotelian physics with astronomical observations highlight the intellectual tensions of his time. The prevailing Aristotelian view of the cosmos, with its emphasis on uniform circular motion and its geocentric framework, presented a challenge to astronomers seeking to explain the complexities of planetary motion. Samarcandi, while adhering to the fundamental principles of Aristotelian cosmology, sought to accommodate the observed deviations from uniform circular motion by refining the geometrical models used to represent planetary orbits. His work, along with that of other astronomers in the Maragha school, contributed to a growing body of evidence that would eventually challenge the Aristotelian worldview. The accumulation of increasingly accurate astronomical data, coupled with the development of more sophisticated mathematical techniques, gradually eroded confidence in the traditional geocentric model. While Samarcandi himself did propose a heliocentric model, his contributions to the refinement of the Ptolemaic system provided essential groundwork for later astronomers who would ultimately overturn the geocentric paradigm. The historical significance of Samarcandi's work lies in its contribution to the long and arduous process of unraveling the mysteries of the cosmos. His meticulous observations, his sophisticated mathematical techniques, and his unwavering commitment to reconciling theory with observation all played a part in shaping the development of astronomy. His legacy endures as a reminder of the power of human intellect to probe the secrets of the universe and to advance our understanding of the world around us. Samarcandi's intellectual curiosity extended beyond the celestial realm, encompassing the intricacies of light and vision. His work in geometric optics represents a significant contribution to understanding the fundamental principles governing the behavior of light, building upon the foundations laid by earlier scholars, most notably Ibn al-Haytham, also known as Al-Hazen. Al-Hazen's Book of Optics provided a comprehensive framework for understanding vision as a process of light rays emanating from objects and entering the eye, a concept that profoundly shaped Samarcandi's own investigations. Samarcandi grappled with several key problems in optics. He sought a deeper understanding of the laws of reflection and refraction, aiming to precisely describe how light changes direction when encountering different surfaces and media. He explored the formation of images by lenses and mirrors, endeavoring to explain how these optical elements manipulate light rays to create focused or distorted representations of objects. Furthermore, he investigated the very nature of light itself, contemplating its properties and behavior as it propagates through space and interacts with matter. Samarcandi's methodology in optics was rooted in geometry. He relied heavily on diagrams and geometric proofs to illustrate and validate his theories. His approach involved tracing the paths of individual light rays as they interacted with lenses, mirrors, and other optical elements. By applying geometric principles, he could derive mathematical relationships that describe the angles of incidence and reflection, the focal lengths of lenses, and the magnification produced by optical systems. It is plausible, though less well documented, that Samarcandi also conducted experiments to verify his theoretical predictions, potentially using rudimentary lenses and mirrors to observe the behavior of light firsthand. One specific example of Samarcandi's work in optics can be found in his treatise on the subject, where he presented a series of propositions and theorems regarding the behavior of light. He formulated rules governing the reflection of light from plane and curved surfaces, demonstrating how the angle of incidence equals the angle of reflection. He also explored the refraction of light as it passes from one medium to another, such as from air to glass, deriving mathematical relationships that describe the change in direction of the light rays. Samarcandi's geometric approach to optics While distinct from the later development of physical optics, laid important groundwork for understanding light's behavior. His meticulous, geometric analysis of lenses and mirrors contributed to the development of more sophisticated optical instruments. The legacy of his work is evident in the subsequent advancements in lens grinding techniques and optical instrument design. His careful study of refraction, for example, provided a foundation for understanding how lenses could be shaped to correct vision problems, leading to the creation of more effective eyeglasses and other vision aids. The enduring historical significance of Samarqandi's optical work lies in its contribution to the broader scientific understanding of light and vision. His rigorous application of geometry to optical phenomena helped to establish optics as a quantitative science, paving the way for later researchers to build upon his findings and develop more comprehensive theories of light. His emphasis on observation and mathematical analysis exemplify the scientific spirit of the era, fostering a culture of inquiry and experimentation that would ultimately lead to significant breakthroughs in our understanding of the natural world. Samarqandi's optical investigations also directly influenced the work of other scholars. Kamal al-Din al-Farsi, a contemporary scientist, drew upon the optical theories developed within the Maragha school, including Samarqandi's contributions to formulate his explanation of the rainbow phenomenon. Al-Farsi's analysis of the rainbow involved tracing the paths of sunlight rays as they entered raindrops, underwent refraction and reflection, and then exited the raindrops to reach the observer's eye. His explanation, which built upon the geometric optics developed by Samarqandi and others, provided a scientifically sound account of this colorful atmospheric phenomenon. Moreover, Samarqandi's meticulous approach to optics, emphasizing geometric analysis and mathematical rigor, served as a model for later generations of scientists. His work demonstrated the power of combining theoretical reasoning with empirical observation to unravel the mysteries of the natural world. This influence extended beyond the immediate circle of scholars at Maragha, contributing to the broader development of scientific methodology in the centuries that followed. His legacy endures as an example of the enduring impact of careful observation, rigorous analysis, and the pursuit of knowledge for its own sake. His optical studies, though perhaps less celebrated than his astronomical achievements, represent a significant facet of his multifaceted intellectual contributions. Direct hit specific instructions for this part 4 of 5's current part focus: explore the intellectual environment of the Maragha Observatory and its role in shaping Samarqandi's scientific methodology. Detail specific scientific instruments and resources available at Maragha. Explain how the collaborative environment and access to extensive astronomical data influenced his research. Discuss the specific problems he faced in using these instruments and how he addressed them. Analyze Samarqandi's specific contributions to the observatory's scientific output. Beyond just his individual works, direct influence person-to-person Mayyad al-Din al-Urdi, whose engineering skills were instrumental in the construction of the instruments at Maragha, which Samarqandi would have used. Direct influence on others person-to-person scholars who visited or studied at Maragha, such as those from China and other parts of Asia, who carried the observatory's scientific knowledge and techniques back to their home countries. Content to explicitly exclude from this part: do not delve into the political history of the Mongol Empire or its impact on scientific patronage beyond the direct establishment in support of the Maragha Observatory. Avoid broad generalizations about the golden age of Islam unless directly relevant to specific scientific activities at Maragha. Do not discuss philosophical or religious debates that did not directly impact the scientific work conducted at the observatory. Context from previous part: his optical studies, though perhaps less celebrated than his astronomical achievements, represent a significant facet of his multifaceted intellectual contributions. Hint about next part: the subsequent part 5 will delve into summarize Samarqandi's lasting legacy in mathematics and astronomy. Discuss the specific ways his work influenced later scholars and scientific developments. Assess the overall significance of his contributions to the scientific revolution. Conclude with a reflection on the enduring value of his intellectual pursuits. Strict reminder: adhere absolutely to all negative constraints regarding not X but Y patterns, repetitive phrasing, and especially the complete exclusion of the words not and just all parts must be free of them. Crucial reminder on content: provide original academic insights and direct, verifiable examples of influence, who influenced them, who they influenced. Avoid generalities about historical context or broad contributions without specific elaboration. Generate approximately 1,150 words of essay content for part 4 based on the directives above. Remember to ensure perfect continuity with the previous part, seamless transitions, and absolute adherence to all negative constraints. Samarqandi's contributions to astronomy and optics gain even greater significance when viewed through the lens of the Maragha Observatory, an institution that served as a crucible for scientific innovation during the 13th century. This observatory, established under the patronage of Al-Urdi Khan, provided an unparalleled environment for astronomical research, fostering a collaborative spirit and offering access to resources previously unimaginable. The intellectual atmosphere at Maragha profoundly shaped Samarqandi's scientific methodology, enabling him to refine his observational techniques and deepen his theoretical understanding of the cosmos. The observatory itself was a marvel of engineering and scientific design. Mayyad al-Din al-Urdi, a skilled engineer and astronomer, played a crucial role in its construction, designing, and overseeing the creation of a suite of sophisticated instruments. These included a massive neural quadrant used for precise measurements of the positions of celestial objects as they crossed the meridian. Its sheer size allowed for greater accuracy in determining stellar altitudes and transit times. There was also an armillary sphere, a complex arrangement of rings representing the celestial equator, ecliptic, and other important astronomical circles, enabling astronomers to visualize and measure the positions of stars and planets in 3 dimensions. The observatory housed astrolabes of various sizes and designs, portable instruments used for determining the time of day, the positions of celestial objects, and for astrological calculations. These instruments, along with sundials and other specialized devices, provided Samarqandi and his colleagues with the tools necessary to conduct cutting-edge astronomical research. Beyond the physical instruments, the Maragha Observatory boasted an intellectual infrastructure that was equally impressive. It housed a vast library containing manuscripts from across the Islamic world and beyond, encompassing works of mathematics, astronomy, optics, and philosophy. This extensive collection provided scholars with access to the accumulated knowledge of previous generations, allowing them to build upon existing theories and develop new insights. The observatory also attracted scholars from diverse backgrounds, fostering a vibrant intellectual exchange. Astronomers from Persia, Syria, and other regions of the Islamic world collaborated on research projects, sharing their expertise and perspectives. Furthermore, the observatory maintained connections with scholars in other parts of the world, including China, facilitating the transmission of scientific knowledge across cultures. The collaborative environment at Maragha was particularly conducive to scientific progress. Astronomers worked together to collect and analyze data, sharing their observations and insights. This collaborative approach allowed them to identify and correct errors, improve the accuracy of their measurements, and develop more robust theories. The observatory also served as a training center for aspiring astronomers, providing them with the opportunity to learn from experienced scholars and contribute to ongoing research projects. This emphasis on collaboration and mentorship ensured the continuity of scientific knowledge and fostered the development of new generations of astronomers. Samarqandi benefited immensely from the resources and intellectual environment at Maragha. The precise instruments available at the observatory allowed him to refine his observational skills and collect more accurate data than would have been possible elsewhere. For instance, the large mural quadrant enabled him to make highly precise measurements of the solar parameters, contributing to his development of new astronomical tables. The collaborative atmosphere at Maragha exposed him to diverse perspectives and methodologies, broadening his understanding of astronomy and optics. He learned from his colleagues, shared his own insights, and contributed to the collective effort to improve astronomical knowledge. The use of these instruments presented challenges, however. The sheer size and complexity of the mural quadrant, for example, required careful calibration and maintenance to ensure accuracy. Environmental factors, such as temperature variations and atmospheric conditions, could also affect the precision of measurements. Samarqandi and his colleagues developed sophisticated techniques to mitigate these challenges, employing careful observational protocols and applying mathematical corrections to their data. Their meticulous approach to data collection and analysis reflects a commitment to scientific rigor that was characteristic of the Maragha school. Samarqandi's contributions to the observatory's scientific output extended beyond his individual works. He played a key role in the development of the Ilkhanic Tables, a comprehensive set of astronomical tables that were compiled at Maragha. These tables provided accurate predictions of the positions of the sun, moon, and planets, as well as other important astronomical data. Samarqandi contributed to the mathematical and computational work required to produce these tables, applying his expertise in geometry and trigonometry to refine the underlying models. These tables were a monumental achievement, representing the culmination of years of research and collaboration at the observatory, and they became a standard reference work for astronomers throughout the Islamic world and beyond. The influence of the Maragha Observatory extended far beyond its immediate geographical location. Scholars who visited or studied at Maragha carried the observatory's scientific knowledge and techniques back to their home countries, disseminating its innovations throughout the world. For example, astronomers from China traveled to Maragha to learn from their Islamic counterparts, and they subsequently introduced Maragha's astronomical models and instruments to Chinese astronomy. This exchange of knowledge contributed to the advancement of astronomy in both cultures, highlighting the observatory's role as a center for international scientific collaboration. The emphasis on precise measurement and empirical observation, championed by scholars like al-Biruni, deeply influenced the Maragha school's methodology, including Samarqandi's own approach, fostering a commitment to rigorous data collection and analysis. The legacy of the Maragha Observatory lies in its contribution to the development of a more empirical and mathematically rigorous approach to astronomy. The observatory's emphasis on precise observation, collaborative research, and the application of mathematical models laid the foundation for future advances in the field. Samarqandi's work, deeply intertwined with the intellectual environment of Maragha, exemplifies this legacy, showcasing the power of collaboration, rigorous methodology, and access to advanced instruments in advancing scientific knowledge. Samarqandi's enduring impact on the history of astronomy and optics resides in his meticulous refinement of existing knowledge and his commitment to observational accuracy. His contributions, while firmly rooted in the Ptolemaic tradition, reflect a dedication to improving the precision of astronomical models and the understanding of optical phenomena. His treatise on instruments serves as a testament to his practical skills and his understanding of the tools astronomers use to probe the cosmos. The meticulous descriptions and instructions contained within this work provided valuable guidance to subsequent generations of astronomers, enabling them to construct and utilize instruments with greater effectiveness. His contributions extended beyond instrumentation. Samarqandi's engagement with existing planetary models, particularly those of Ptolemy, demonstrates a critical and inquisitive approach. He sought to address inconsistencies and improve the accuracy of these models through careful observation and mathematical analysis. While he operated within the framework of geocentric cosmology, his efforts to refine the parameters of planetary orbits and to account for observed celestial phenomena represent a significant step forward in the pursuit of astronomical precision. The long-term influence of Samarqandi's work can be traced through the transmission of his ideas and techniques to other scholars in the Islamic world. His writings, along with those of his colleagues at the Maragha Observatory, became part of the standard curriculum for aspiring astronomers. Scholars working in later centuries drew upon Samarqandi's observations, calculations, and instrumental designs to further refine astronomical models and to make new discoveries. Specific examples of this influence can be seen in the work of astronomers working in the Timurid Empire, where the legacy of Maragha continued to inspire scientific inquiry. Ulugh Beg, a Timurid ruler and astronomer, established an observatory in Samarkand that consciously emulated the model of Maragha, drawing upon the knowledge and expertise accumulated at the earlier institution. The emphasis on precise measurement and empirical observation fostered at Maragha became a hallmark of Timurid astronomy, contributing to the creation of highly accurate star catalogs and planetary tables. The potential influence of Samarkandi's work on Renaissance astronomy remains a subject of scholarly debate. While direct evidence of transmission is limited, it is plausible that some of his ideas and techniques may have found their way to Europe through various channels. The translation of Arabic astronomical texts into Latin during the Middle Ages provided European scholars with access to a wealth of knowledge accumulated by Islamic astronomers. It is conceivable that Samarkandi's contributions, along with those of other Islamic scholars, may have indirectly influenced the development of astronomical thought in Europe, particularly in the areas of instrumentation and observational techniques. However, establishing definitive links requires further research and analysis of historical sources. One must acknowledge the limitations of Samarkandi's work in light of modern scientific understanding. His adherence to geocentric cosmology, rooted in the Aristotelian physics of his time, prevented him from fully grasping the true nature of the solar system. The development of heliocentric models by Copernicus and others in the 16th and 17th centuries revolutionized our understanding of the cosmos, rendering the geocentric framework obsolete. Furthermore, Samarkandi's reliance on traditional observational methods, while impressive for their time, was limited by the technology available to him. The invention of the telescope and other advanced instruments in later centuries enabled astronomers to make far more detailed and accurate observations of celestial objects, leading to profound discoveries that were beyond the reach of Samarkandi and his contemporaries. Despite these limitations, Samarkandi's contributions remain significant within their historical context. He played a crucial role in refining and preserving classical astronomical knowledge, transmitting it to future generations of scholars. His commitment to mathematical rigor and observational accuracy helped to improve the precision of astronomical models and to advance the understanding of optical phenomena. His work exemplifies the spirit of scientific inquiry that characterized the golden age of Islamic science, showcasing the power of collaboration, meticulous observation, and mathematical analysis in advancing human knowledge. The emphasis on accuracy and observation, championed by Samarkandi and his colleagues at Maragha, resonates deeply with the modern scientific process. The scientific method, as it is practiced today, places a premium on empirical evidence, quantitative analysis, and the rigorous testing of hypotheses. Samarkandi's dedication to these principles, even within the limitations of this historical context, foreshadows the values that underpin modern science. The pursuit of knowledge requires a steadfast commitment to accuracy, a willingness to challenge existing assumptions, and a relentless pursuit of empirical verification. The legacy of Samarkandi serves as a reminder of the importance of these values in the advancement of scientific understanding. Samarkandi's place in the history of science is not that of a revolutionary innovator who overturned existing paradigms, but rather that of a meticulous scholar who refined and advanced existing knowledge. He embodies the spirit of incremental progress, demonstrating the value of careful observation, rigorous analysis, and the patient accumulation of data. His contributions, while perhaps less dramatic than those of some other figures in the history of science, are nonetheless essential to the overall narrative of scientific progress. He stands as a testament to the enduring power of human curiosity and the unwavering pursuit of knowledge. The meticulousness with which Samarkandi approached his work serves as an example for contemporary scientists in an era marked by rapid technological advancements and an overwhelming abundance of data. The importance of careful observation and rigorous analysis cannot be overstated. The ability to discern meaningful patterns from noise, to identify sources of error, and to critically evaluate the validity of data remains essential to the scientific process. Samarkandi's legacy reminds us that scientific progress is not simply about collecting more data, but also about developing the skills and the mindset necessary to interpret that data accurately and to draw meaningful conclusions. Moreover, Samarkandi's contributions highlight the importance of collaboration in scientific research. The Maragha Observatory, where he conducted much of his work, was a center for international scientific collaboration, bringing together scholars from diverse backgrounds and intellectual traditions. This collaborative environment fostered the exchange of ideas, the sharing of expertise, and the cross-fertilization of knowledge. The success of the Maragha Observatory underscores the value of creating inclusive and collaborative research environments that encourage the participation of scholars from all backgrounds. The enduring value of Samarkandi's commitment to mathematical rigor and observational accuracy lies in its contribution to the development of a more empirical and quantitative approach to astronomy. His meticulous measurements, his careful calculations, and his detailed descriptions of astronomical instruments helped to transform astronomy from a largely theoretical discipline into a more data-driven science. This emphasis on empirical evidence and quantitative analysis paved the way for future advances in astronomy and other scientific fields. In conclusion, Jamal al-Samarkandi's legacy resides in his dedication to refining existing knowledge, his commitment to observational accuracy, and his contributions to the development of a more empirical approach to astronomy. While his work was limited by the scientific understanding of his time, his meticulousness, his collaborative spirit, and his unwavering pursuit of knowledge serve as an inspiration to scientists today. His place in the history of science is that of a meticulous scholar who helped to preserve and advance classical knowledge, laying the foundation for future discoveries and contributing to the ongoing quest to understand the universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.